Okay, we're here on problem number 18, and this one's pretty easy. To determine the height of the bridge above the water, a person drops a stone and measures the time it takes for it, that would be the stone, to hit the water. If the time is 2.3 seconds, what is the height of the bridge? So I'm basically on a bridge here and I'm dropping a stone, it falls down and hits the water. So I'm dropping it, not throwing, so my initial velocity is 0. Time here is what? 2.3 seconds. So come over here to my velocity time curve, and what do I know? Oh, I did it again, didn't I? We're going down, so I'm working in the bottom quadrant because we're going negative. Velocity starts 0 and it's going to increase in magnitude but becoming more negative. I know the acceleration is 2.3. Oh, that's the time. I know the acceleration is 9.8 meters per second squared because of course it's free fall. And I know that after some period of time, 2.3 seconds, it's going to hit the ground, but I don't know what the velocity is here. But I do know, of course, I started 0. Now, what am I looking for? I'm looking for height of the bridge, so I basically want to know how much distance it travels during this time that it's traveling here. Well, this should be pretty easy. I know my acceleration. I know the time. Do I know velocity? No. But do I know an equation that relates acceleration and distance and time? You should be pretty familiar with this equation by now because we've used it a couple of times. Come to our constant acceleration chart. This is velocity and time. That's not the one I want because I don't know my final velocity. Distance, velocity, and time. Is that the one I want? Maybe. Velocity and distance. Again, I can't use this because I don't know my final velocity. So which one am I going to use? I'm going to use this one. So bring the initial distance over here again. I'm going to rewrite this so it's delta x equals v initial delta t plus 1/2 a delta t squared. Don't forget that squared. Okay, this goes to 0 because I'm dropping it, so I'm initially starting at a velocity of 0. So my formula becomes very easy. Delta x is 1/2 a delta t squared. Distance is what I'm trying to find, so I don't need to do any algebra rearrangements. That makes it convenient. 1/2 acceleration 9.8 meters per second squared. Time, well, that's pretty easy, 2.3 seconds. Don't forget to square it. Units cancels units, so I should have 9.8 divided by 2 times 2.3 squared, 25.9 meters. And obviously C is the answer they're looking for because they're looking for me to round it, and there we go. So let's go on to the next problem here, problem number 19. Problem number 19 takes me to this sheet, and I need a clean sheet of paper. Hold on a second, I'm out of paper. Oh, there. Okay, I'm back. I got some paper. Okay, problem number 19, otherwise known as problem number 92. Ooh, an astronaut. We're in space. An astronaut stands by the rim of a crater on the moon where the acceleration of gravity is blah and there is no air. To determine the depth of the crater, she Yay! She drops a rock and measures the time it takes for it to hit the bottom. The time is 6.3 seconds. What is the depth of the crater? Alright, so this is problem number 19. Here I am standing on the edge of a crater, and I drop a rock, and it falls, falls, falls. Initial velocity, I drop it, I don't throw it, so initial velocity equals 0. And of course I know acceleration is 1.6 meters per second squared. What am I looking for? I'm looking for the time. Oh, I measured the time, 6.3 seconds. I want to know the distance it falls. So again, I'm going to go to my velocity time curve. How many times am I going to do that? I'm going down, so I'm working below in the negative range. Velocity starts at 0 and is going to go down at a rate of 1.6 meters per second squared. I know at some point here, 6.3 seconds later, I will hit the ground. I don't know what the velocity is, and honestly I don't really care because I'm looking for distance. So, what equation do I know that will relate time, acceleration, and distance, which is what I want to find? And I can hear you all right now. You're telling me to go to which equation? Yeah, the same one we've been using a couple of times now. So you should be able to do this from memory, right? Delta x equals vi delta t plus 1/2 a delta t squared. Don't forget the squared. Okay, let's substitute in. My initial velocity is what? It's 0, so that goes to 0, which makes it really nice. So it becomes 1/2 a delta t squared. Let's substitute in. 1/2 times my acceleration, 1.6 meters per second squared, times delta t, which is 6.3 seconds. Don't forget to square it. Units cancel. Let's calculate and see what we have here. .6 divided by 2, could have done that in my head, times 6.3 squared equals 31.75 blah 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 meters, which obviously when I look at significant figures takes me to 32. Answer D, and that is the one they want.